Okay, hi everyone. So now we're going to talk about taking natural logs and putting them in application questions. So this all might look really, really complicated at first, but it's just plugging numbers into equations that are already given to us. It's so easy. So, for instance, we're going to start, there's two kinds. There's space and biology. So we're going to start with space. So it's going to give us this formula. V equals negative 0.0098 t plus c is natural log r, or of natural log r, where v is the velocity of the rocket, t is the firing time, c is the velocity of the exhaust, and r is the ratio of the mass of the rocket filled with fuel to the mass of the rocket without fuel. So it's gonna now give us some variables and we're gonna have to plug it into the equation. So a booster rocket for a spacecraft has a mass ratio of about 15, an exhaust velocity of 2.1 kilometers a second, and a firing time of 30 seconds. Can the spacecraft achieve a stable orbit of 300 kilometers above Earth? And I know this right here just kind of comes out of the blue because there's nothing here about distance or anything like that, but that's just them kind of trying to trick us. A stable orbit of 300 kilometers above Earth is 7.7 kilometers an hour. So it's just asking us, will the velocity be above 7.7 kilometers an hour? So let's look at the variables we have. So we don't have velocity. We're trying to solve it, but we're asking ourselves, will it reach 7.7 kilometers an hour? T is 30 seconds, C is 2.1 kilometers a second, and R is 15. So we plug it into the equation that was given to us and we get this. Negative 0.0098 times 30 plus 2.1 natural log is of 15. So first we're going to do these two numbers because these are easy numbers. We're just going to multiply them and we get negative 0.294. And then when you plug 2.1 natural log of 15 into the calculator, you get 5.686. And next all you have to do is add these numbers. So you add the numbers together and you get the velocity of 5.392 kilometers an hour. So no, it does not reach 7.7 kilometers an hour. And we're done. We answered the question. So again, it looked complicated. It was really wordy, but it's just plugging these numbers, including a natural log, into an equation and solving. So next we're going to move on to biology. And this is a different formula. It's more complicated simply considering that there's two natural logs now, but we're going to work this out. So the formula H equals 1 over R times natural log P minus natural log A models a number of hours it takes bacteria to culture to decline, where H is the number of hours, R is the rate of decline, P is the initial bacteria population, and A is the reduced bacteria population. So a scientist determines that an antibiotic reduces a population of 20,000 bacteria to 5,000 in 24 hours. Find the rate of decline caused by the antibiotic. So it's asking us for the rate of decline. We're going to have to restructure this equation, and we will, but first we're going to define our variables. So R is what we're looking for. H is 24 hours, P is 20,000, and A is 5,000. So let's plug that in to our new equation. So this is our new equation where we isolate R. Now it's R equals natural log P minus natural log A over H. So, sorry. When we plug that in, we get this. R equals natural log of 20,000 minus natural log of 5,000 all over 24. Now, let's take account this log rule. This is a very important log rule, which says if you're subtracting two logs of the same base, you can divide them. So let's do that with this one. Because remember, they have the same base. They have the base of E. A natural log has the base of E. So it becomes natural log of 20,000 over 5,000. And when we plug that into our calculator, we get 4. 20,000 divided by 5,000 is 4. And I simply simplified 4 to 2 to the power of 2 to make this a bit easier for us, because when there's an exponent in a natural log, we have to move the base to the outside. So now it's 2 natural log of 2. And remember, we can't forget this over 24. We kind of forgot it for a quick second, but now it's back. So this all simplifies to 2 natural log of 2, all divided by 24. So we plug that into our calculator, and we get this number. So this is the rate of decline, and we have our answer. So hopefully you understood that. Now we're going to move on to a different question. A laboratory assistant tests an antibiotic that causes a rate of decline of 0.14. How long should it take for a population of 8,000 bacteria to shrink to 500? So let's look at our variables. R is 0.14. H is what we're trying to find. P is 8,000. And A is 500. So let's plug that into the equation. The first thing we're going to do is we're just going to divide 0.14, 1 by 0.14, because those are just numbers. It's really easy to do. And we get 7.143. So now let's simplify this, the 2 natural logs. We're going to apply that log rule we just learned, which is to divide these 2 numbers and put them in the same log. And so we get 7.143 times natural log of 8,000 over 500. Now when we divide 8,000 by 500, we get 16. So now all we have is 7.143 times natural log of 16. And we just plug that into our calculator, and we get this beautiful number. H, which is the number of time, is equal to 19.805 hours. So I know this all looks really complicated. It was really daunting to me at first, but it's just plugging numbers into calculators and remembering simple log rules. So I hope this made sense. Thank you.